Hey learners, welcome to Unit 3 of Data Structure series. In this unit, we are diving into something fascinating, that is trees. No, not the one outside, but the one inside programming. Trees are an essential part of data structures, and trust me, they are everywhere, from databases to file systems, even in network routing. Ready to branch out and learn? Let's get started. Alright, let's break it down. A tree is a nonlinear data structure that organizes data in a hierarchical way. Think of it as a family tree with a root at the top and branches connecting various nodes. Each node can have subtrees, or it can stand alone as an empty tree with no nodes. Unlike arrays or linked lists, trees aren't linear, they are hierarchical, which makes them super useful for organizing data efficiently from databases to file systems. Trees are a go-to tool. Excited to learn more? Let's explore them further. Now that we know what trees are, let's get familiar with the basic terms used in trees structures. The root is the topmost node. Think of it as the starting point of the tree. It has no parent. An edge is like a bridge connecting two nodes. A parent node is that one or more child nodes, and those nodes are called children. Nodes that share the same parent are siblings. Moving further, a leaf is a node with no children. It's also called an external node. On the other hand, an internal node has at least one child. The degree of node tells us how many children it has. The level indicates how far a node is from the root, while the depth is the number of edges from the root to a specific node. The height of a tree or a node is the longest path from that node to the leaf. Finally, a path is a sequence of nodes and edges connecting two nodes, and a subtree is simply a smaller tree within the main tree, formed from a node and its descendants. That's the basic terminology. These concepts are crucial as we explore trees further. Let's keep going. Now let's talk about a special type of a tree, the binary tree. In a regular tree, nodes can have any number of children, but in a binary tree, every node can have a minimum of two children. These are referred to as the left child and the right child. Simply put, a binary tree is a tree structure where each node has either 0 children, 1 child, or 2 children, but never more than 2. This makes it easier to organize and work with data in a structured way. Here an example to visualize. Imagine a node at the top. This is the root. It can have at most two branches, one pointing to the left child and other to the right child. That's the essence of a binary tree. Binary trees are the foundation for many advanced concepts, so understanding them is key. Ready to see one in action? Let's move ahead. Now, let's explore the different types of binary trees. First up, the strictly binary tree. In a binary tree, nodes can have a maximum of 2 children. But in a strictly binary tree, the rule is stricter. Every node must have exactly 2 children or none at all. In other words, every internal node has exactly 2 children, while leaf node have none. Here the formal definition. A strictly binary tree, also known as fully binary tree or proper tree or two tree, is a binary tree in which every node has either 2 or 0 children. Interestingly, this structure is widely used to represent mathematical expressions, making it a valuable tool in computer science. Let's look at an example to understand this better. Next, let's talk about the complete binary tree, also known as a perfect binary tree. In a binary tree, every node can have a maximum of 2 children, but in a complete binary tree, there is an additional rule. Every internal node must have exactly 2 children, and all leaf nodes must be at the same level. There is a specific pattern in complete binary trees. At each level, the number of nodes follows the formula 2 raised to the level. For example, at level 2, there are 2 square equals to 4 nodes. At level 3, there are 2 power 3 equals to 8 nodes. This structure ensures that the tree is perfectly balanced, making it efficient for operations like searching and inserting data. Complete binary trees are widely used in applications like heap and priority queues. Want to see an example? Let's visualize one next. Finally, let's discuss the extended binary tree. Sometimes a regular binary tree doesn't follow the structure of a full binary tree. To convert it into a full binary tree, we add dummy nodes wherever needed. These dummy nodes ensure that every internal node has exactly two children. The resulting tree after adding these dummy nodes is known as extended binary tree. This approach helps standardize the structure, making it suitable for certain algorithms and applications where a full binary tree is required. It's a sample yet effective way to transform a binary tree into a strictly binary structure. Want to see how this conversion works? Let's take a look. Would you like to visualize representation showing how dummy nodes are added to create an extended binary tree? This is the image. Please observe this image. Let us know some important properties of binary trees. First, a binary tree can be empty, meaning it has no nodes at all. Next, each node in a binary tree has exactly two subtrees, which can be empty. Also, the subtrees or children are ordered, meaning their positions matter. There is a left child and a right child. Now, here is an interesting fact. A binary tree with n elements will always have n minus 1 edges. When it comes to the height of a binary tree of height h has at least h elements and at most 2 power k minus 1 elements. The height of a binary tree with n nodes is at least log 2 base n plus 1 and at most n. Here how it works. At height 0, there is at most one node, that is the root. At height 1, there is at most two nodes, the root's children. At height 2, there are at most 4 nodes and so on. Lastly, in a binary tree, the number of leaf nodes is always one more than number of nodes with two children. These properties are what make binary trees so versatile and efficient in computer science. Now let's talk about how binary trees are represented in memory. There are two main methods to represent a binary tree. First one is array representation. In this method, the binary tree is sorted as an array. The root node is sorted at index 1 and its children are placed at specific indices based on their positions. The left child of node at index I is sorted at 2i and the right child is stored at 2i plus 1. The second one is linked list representation. Here each node is represented as an object or structure that contains the data and pointers. Its left child and right child. This method is more flexible, especially for dynamic trees, because it doesn't require contiguous memory. Let's consider an example binary tree to see this representation in action. These methods are fundamental to understanding how binary trees are implemented in programming. Let's dive into array representation of binary trees. In this method, we use a one-dimensional array to represent the entire binary tree. Each node is stored at a specific index and its position determines the locations of its children and parent. Here how it works. To represent a binary tree of depth n, we need an array of maximum size 2 power n plus 1 minus 1. The root node is placed at index 1. For a node at index I, the left child is stored at 2i and the right child is stored at 2i plus 1. Using this structure, we can store and navigate the tree efficiently using a simple arithmetic on indices. Consider the binary tree we discussed earlier. Let's see how it looks in an array representation. This method is great for complete or perfect binary trees as it ensures minimal wasted space. Now let's talk about the linked list representation of binary trees. In this method, we use a doubly linked list to represent the tree. Each node in the list consists of 3 fields. The first field stores the address of the left child, the second field stores the actual data, the third field stores the address of the right child. This structure allows us to navigate easily between parent and child nodes, making it highly flexible for dynamic tree operations. Here what a single node looks like in the linked list representation. The left pointer links to the left child, the right pointer links to the right child, and the data field holds the node's value. Using this representation, let's see how our earlier example binary tree looks. This method is particularly useful for sparse tree because it doesn't waste memory like array representation might. That's wrap up our today's video on binary tree representation. In our next video, we will dive into binary tree traversal and binary search trees and explore how they work. Thanks for watching. If you found this video helpful, don't forget to like, share, comment and subscribe for more content. See you all in my next video. Thank you for watching.